So this application example, as you can see on your screen already, what it has a composite beam made of two different materials. So you see the top part is material 1, which is wood over here, and in the bottom you have a smallish steel plate which is of 12 mm thickness over here, and the wood, the height of the wood is 150 mm. What you are also given are the modulus of elasticity, and now you know why you are given this, because you have to calculate the modular ratio n, right? And what the problem asks you is to find that given this beam is subjected to a 6 kilonewton meter bending moment, positive bending moment, so sagging, right? Now you have to have a bending moment to have stresses, otherwise you will not have stresses. So for a positive bending moment of 6 kilonewton meter, what is the maximum and the minimum stresses in the wood? Now we can roughly tell the maximum and the minimum is compression. So if it's a sagging, so the top part will be in compression, and this part, this interface over here, will be in tension, where we'll have the maximum stresses. And similar for the steel. So for the steel, as you can tell, if this is the neutral axis over here, so in this if I just go ahead and say that this is my neutral axis, so along that particular line, and below that the whole beam will be in tension. So both the maximum and the minimum stresses in steel will be in tension over here, right? So let's maybe reiterate and take a look at the problem. So you are essentially given a beam like this over here. So say the top part is wood and the bottom part is steel, right? So now you are given that I'm just reiterating the problem, just trying to imagine it with the beam that I have over here, and then you are giving a positive bending. Positive means sagging, so it is sagging like this. So as you can see that the top part is in compression and the bottom part is in tension, and the neutral axis is somewhere over here. Now the neutral axis, you cannot from the problem example that you see, the neutral axis you cannot simply find by taking from this composite section, because the neutral axis is not going to coincide with the centroid of the composite section that you have. It coincides with the centroid of the transformed section, as we had seen, right? So now let's go ahead and try to do this problem. So remember that the first step of our using the method of transformed sections to solve composite beams is to calculate the modular ratio. So here the problem, what we're going to do before we start punching in the numbers, is that we are going to take this beam. It is made of partly of wood and partly of steel. We are going to transform this beam to a beam which is made of one single material. There are two ways to do it. You can either transform the wood to the steel, or you can transform the steel to the wood. So typically what I prefer doing is that transforming the stiffer material to the less stiff. So essentially you have a widening. So here what I'm going to do, I'm going to transform the steel to the wood. So what you expect to see is the bottom part to be widened. Remember, the height always stays the same because the strain profile stays unchanged. Or if you want to transform the wood to the steel, what you will essentially have, that this wood and this particular width is going to shrink. So you are going to have a T kind of a beam. So you will have this one over here and a small shrunk out portion of the wood now converted to steel. So let's go ahead using the first transformation, that we are converting the steel to the wood. So for that we have to calculate, remember, first is the modular ratio. So let us calculate the modular ratio over here. So I'm going to write the modular ratio. N is simply E2 divided by E1 over here. So that is 210 divided by 10.5. So now if you calculate this one, what you essentially get is 20. Right? So my modular ratio N is 20. So I have calculated my modular ratio over here. So now how am I going to use this modular ratio? Remember, the second or the third step is that the width of the material 2 now increases. So the material 1 stays the same. So material 1, the section that you see over here, it stays the same. Only for the material 2 the width increases. So let me go ahead and put the picture here for material 2. Now this whole problem is from one of your textbooks, the Gear and Goodness. So if you want, you can take a look at that as well. So let me now go ahead and paste the picture of the transformed section that is there. So here now I have the transformed section. So you see in the transformed section, so the entirety is made of material 1. So here you had material 1, material 2, and I've converted material 2 to material 1. So as you can tell, that what was that initial width of 100 mm over here, So now that width, so what was B initially, so what was your B initially, it now becomes, you know, n times B over here, because you're increasing the width over here. So that means that what was initially my 100 mm for the steel plate, now I've converted to material 1, and the equivalent width is going to be n times 100, so that is 20 times 100, so that is, you know, 2000 mm, or essentially 20 meters, which is your this part over here. So your top part stays intact, top part 100 by 150 made of material 1, it stays intact. Only the bottom part over here, where the width which was 100 mm, now it has been bumped up to n times 100, that is sorry, this is not 20 meters, this is 2 meters over here. It has been bumped up to 2 meters over here, so you have a 2-meter thing over here. So now the entire section is now made of material 1. As you can see in the diagram here, it was material 1, material 2 here. Now the entire section is made of material 1. Okay, so now that we have a transformed section where the entire section is made of one single material, we can go ahead and, you know, apply our basic principles that now the neutral axis must coincide with the centroidal axis. So that means that I have to find my location of the centroid. So this is the neutral axis which was there in the beam, so this is also now coincides with the centroidal axis that is there. So for that, these are the heights which are given. So this is the height h1 from the top to the centroid, so this is also my centroid now for the transformed section. Remember, it's not the centroid of the original section, it is the centroid for the transformed section. So let me also mark that one over here. So this is my centroid. Let me just write this centroid, as well as this is my, you know, neutral axis over here, right? So for this we have to calculate the h1 and the h2 for the transform section, which is fairly simple, and I'm not going to write out the different equations for that. You just have to, you know, take the moments of the areas about the bottom or at the top or wherever you want to take to calculate h1 and h2. And the h1 and h2 I've computed already. Now another thing that you would need, remember, to calculate your sigma is the formula sigma is my by I. So you have to calculate the area moment of inertia also about the centroidal axis or about the neutral axis for the transformed section, right, which you can also easily calculate. You have, you know, these two separate rectangular chunks, you calculate the area moment of inertia of these individual chunks, and then you apply the parallel axis theorem to compute about the neutral axis. So I'm going to write out the final numbers that we get over here. So what we get, your h1, what we get is h1 comes out to be 124.8 mm. Your h2 comes out to be 37. I have this solved already, or you can take a look at the textbook, the Gear and Goodnow, which is there. And then the I of the transform section, remember, for the transform, not for the original one, the I for the transform section comes out as 89 times 10 raised to 6 mm raised to 4. So I have the basic properties of the basic material set. Now let's me go ahead and try to solve this first part over here, which asks is the maximum and the minimum stresses in the wood. So the maximum, and then I know that the minimum stress means the compressive stresses, which is the negative stress that I have. And for this one, remember that I have, you know, the top part is the wood, so the compressive minimum stress or the compressive is going to happen at the top over here. So that is fairly, you know, straightforward to calculate. So let me, so that I know, so the minimum stress in the wood, it occurs at A, right, at this particular point over here, right, and the maximum is going to happen here because the wood ends at this point C, so it's a maximum tensile stress at C. So the maximum is going to happen at C, right? Now what about for the steel? The steel will be entirety in tension because it is below the neutral axis over here. So the bottom part is the steel. You see the steel is entirety in tension. So the minimum tensile stress, of course, will occur at this interface over here. So it is going to happen at C, and the maximum you know, tensile stress is going to happen at this, the bottommost interface. So that is at B over here. So let's go ahead and calculate that. What I'm going to write over here is that for wood, right, I'm going to have your sigma 1, which is the one representing the material 1 at A, where the minimum stresses occur over here, is going to be equal to what? So now I know it is compressive already, so I'm just going, so don't be bogged down by the signs, it is compressive. I'm just putting a negative over here. It's going to be minus m times this height over here, this is h1 by I, my by I. Simply I've applied the I for the transform section, so that is easy to calculate. Your moment is given as 6 kilonewton meters over here, so it is going to be 6 into 10 raised to 6 times h1 I've calculated, it is 124.8 divided by the I of the transform section, that is 89 into 10 raised to 6. So that will, the number that it will give you is, so sorry, I forgot the negative sign, it will be minus 8.42 MPa, right? Similarly, so this is the minimum stress that you have over here, and the maximum stress is going to happen at this interface C over here. So sigma 1 at C will be similarly 6 into 10 raised to 6. It will positive now because it's tensile, times, you know, this distance from here to here. So that is going to be h2 minus this 12 mm that we see, because we are not altering the height, remember. So it is going to be 37.2 minus, because we calculated h2 as 37.2, minus 12 divided by the I of the transform section, which is 89 into 10 raised to 6, and this one you get as 1.69 MPa. So this is for the wood, right? So for the wood, now we have computed the, this is the minimum and this is the maximum. Now next is for the steel. Now remember, in the method of transform sections, what we do is that we calculate the stresses for material 1 at wherever we need to compute, right, wherever it encompasses the material 2, and then we multiply with the modular ratio n. So for steel, so let's just calculate for steel, right? So for steel, it is going to be what? For steel, the minimum stress occurs at this point C over here. So let's just calculate that. So this is going to be sigma 2, because I'm calculating for material 2 at C is going to be what? Is going to be equal to sigma 1 at C times the modular ratio n. Simple, because the stress for this one, remember, is that linear variation that I have, and this is where, this is the interface where I expect the jump. So this is the interface C, which is shared both by the wood and the steel, right? So here I'm going to calculate sigma 1 times sigma 1 for the material 1 at C, and I'm going to multiply with the modular ratio. So that is nothing but your 1.69, which I have already calculated over here, times your 20. So that comes out as 34 MPa, right? And lastly, it asks for the maximum stress. So the maximum stress, or the maximum tensile stress, in this case it happens at this interface B over here, that is your sigma 2 B will be equal to what? Similar to what we saw, is going to be sigma 1 at B. Although originally the material 1 does not occur at B, but we have now transformed the material 1 to material 2 to entirely consist of material 1 and material, you know, the entirety is in material 1. So I can, for this material 1, which is wood, I can calculate the one at B over here, and I simply have to multiply with the modular ratio n. So sigma 1 at B times n. So I need to calculate this first part over here because I have not calculated it earlier. So it is going to be what? It is going to be 6 into 10 raised to 6 times this height, the whole height h2 now. So that is 37.2. So I'm just simply going to write h2. You can substitute and calculate, divided by the I of the transformed section, times 20. Don't forget that. So that comes out to be around 50.2 MPa. So here for the steel, so this is the minimum and this is the maximum. Now remember that for steel both are tensile, so this is both are tensile, so good to make a note. Whereas for here this is, you know, compressive and this is tensile. So I hope this problem was clear, that how we took this entire material made of material 1 and 2 and converted to that one, but we back calculate to find the stresses using this modular ratio that we have over here. Remember, at the onset of when we started talking about composite beams, we said one of the classic examples of composite beams are everything, all the structures around you, all the reinforced concrete beams that you see are composite beams, because it consists of two dissimilar materials, concrete and the second one is steel over here. So this is a one of the examples where different materials which come together and essentially help you to build all the structures around you. Now if you think of composite beam, so this is a reinforced concrete beam that you have over here, right? You will see that typically that if you see in this beam, your moment is acting like this over here, right? So that means that the bottom part of the beam is in tension, right? So now concrete as a material is very weak in tension, and that is the sole reason why you provide steel within the concrete structures to take the tension, because concrete by itself cannot take the tension. When you will take a course in structural design in your next semester, or maybe a couple of semesters from now, you will learn more about the properties of concrete and the properties of steel, and why steel is absolutely essential to take care of the tension that is there, right? Now here in this beam also you will have a neutral axis somewhere, right? Now what is typically assumed, and this I am saying over and over, and you will hear this a lot more when you take the concrete design, is that when you have a beam that is made of reinforced concrete and you have a neutral axis somewhere within the section, you have a neutral axis, because of this moment you will have a top is in compression and the bottom part is in tension. You'll have a neutral axis over here. Below the neutral axis, concrete is actually so weak in tension. Below the neutral axis, it is assumed that concrete does not contribute at all to taking the stress due to the tensile stresses which might occur in the beam, right? So the entirety of the tensile stress is assumed to be taken by the steel reinforcements that you have over here. Now again, since it's a composite beam, you're talking about two materials, steel maybe with a modulus velocity E2, concrete with a modulus velocity E1, right? And as is sort of conventional and like the way we saw in the previous example, we convert the more stiffer material into the less stiffer material. So essentially you're converting the whole beam into one single material, right? Now since the concrete is not taking any tension, its concrete is going to be cracked over here, the composite section or the transformed section for this one looks a little funny. So this looks something like this over here, where above here, so we are essentially converting the steel, right, into this n times AST that you have over here. So this AST that you see over here, so let me just mark it. So the AST that we see is, so this one is the area of steel, right? And n, as you know, is the modular ratio. So this n, so this one AST is this guy over here, and this n is nothing but the modular ratio, which is nothing but equals to your n equals to the E of steel divided by the E of concrete, right? So what you have done over here, you have transformed the whole material that you see over here into one single material, that is concrete, the top part. Now when you convert, whatever was the original material, whatever part of the beam was the original material stays the same, which is what you have over here. So above the neutral axis, concrete stays as concrete, but below the neutral axis, since you're assuming that concrete is cracked, so essentially there is no concrete, or it does not help in anything in reducing carrying the tension. All the tension is taken by the steel, but now you have to convert the steel into the corresponding material one, that is concrete. So you multiply the area of the steel, the total area that you have, with n, the modular ratio. So that essentially gives you the spread of this entire area over here. Now this method of solving reinforced concrete beams and essentially designing, so see, the whole point of designing is that you're trying to find that to resist a particular tension, how much amount of steel do I need? Do I need 3 bars, 4 bars, or I don't know what is the grade of steel that you need, right? So this method of designing beams used to be a very integral part of what was known previously as the working stress method. Now In the latest code, this has been revised. We have moved on to the ultimate design method, which you will learn a lot more in your concrete design class. So this method is a little bit obsolete because the working stress method is no longer in existence, but I just wanted you to be aware that there was a time when the reinforced concrete beams were also solved using the similar principles of the method of transformed sections.